Yeah. So so we'll finish up chapter 4 today and get into chapter 5 on entire functions. Hopefully get to the sort of like the main tool, which is called Jensen's formula. Somebody's told me that I've scheduled an exam for next Monday. Is that right? Okay, so yes, there's an exam next Monday, is what I hear. I see some looks of consternation. There's also some sort of sorrowful nodding. Okay, so yes, I think I would like to put Phragmen Lindelof as fair game for the exam. So Phragmen Lindelof is the last thing. Anything past Phragmen Lindelof, don't worry about. Okay. Phragmen Lindelof, however, is fair game for the exam. And I'll send out as before a list of topics, and maybe on Wednesday, instead of doing new material, I'll just sort of review the stuff that we've covered since the last exam. Okay, to give you some sense of that. Okay, so Phragmen Lindelof, right, was kind of our first step in Paley-Wiener, right, in the difficult direction of Paley-Wiener, and that is what allowed us to say that the bounds that we had assumed could be strengthened slightly, right? So we had this thing where we were assuming that we had this extension, and then we had this sort of bound, right? So it was we had an entire extension that satisfied this sort of bound, and then Phragmen Lindelof allowed us to replace this with this, right? And it's from there that we played the epsilon of room trick and got that we could actually talk about functions that satisfied an even better bound, and then take limits of those functions to get back to our original function, right? So that was the strategy of Paley-Wiener. But we need to prove the theorem of Phragmen Lindelof. So let me put that up. So okay, so okay, and I'm sure I'm not pronouncing this correctly, but it's okay. Okay, so the notation. We have a sector, right? So S we're using to denote the sector where the principal argument is between negative pi over 4 and pi over 4. Right, so we have the sector. Right. We have this thing, and then we have a function which is you have some function which is holomorphic on S, continuous on the closure of S, and also of size less than or equal to 1 on the boundary, and also satisfies a growth condition. So it satisfies this exponential growth condition in S. Then, in fact, the size of f is bounded everywhere in S. And what we said last time was that this was sort of like maximum modulus principle. But for this unbounded region. Okay. People are copying things down. I'll just wait. Okay. So the idea here is again that we're going to do this sort of like epsilon of room game. So we'll create an epsilon of room. Okay. So what we do is we create these sort of slightly perturbed functions by multiplying our guy by e to the negative epsilon z to the 3/2. Okay, where we use the principal branch of the log. So this z to the 3/2 is going to be just the positive 3/2 root of this times e to the 3 I theta over 2. So this is the using the principal branch of the logarithm. Okay. So what we're going to do is show that in fact the statement is true for all of these guys, and then we're going to let epsilon go to 0, right? So and that will allow us to see that the statement is true for f, right? So these guys are going to be bounded on S, and then let epsilon go to 0, and that gives us that f will be bounded on S. Okay, and the trick is basically to use the decay here to allow us to invoke the maximum modulus principle. Okay, so the decay of this term will sort of overpower the growth of f, right? And because of that, these functions are going to go to 0 as you head off towards infinity, and that will allow us to invoke the maximum modulus principle. Okay, so anyway, let me show you how that goes. Okay. So so the strategy is to show that each of these guys is bounded by 1 in S closure, and so then let epsilon go down to 0, and that will give us for the original function. Okay. So the first thing we're gonna do is show that that each of these things is bounded. Okay. So FEZ is bounded. Okay. And the proof is basically, as I just said, you look at the size of this thing, and you say, well, look, this thing is controlled by this thing times this, right? Times the size of the parts, and we know that this guy is controlled by CE CZ, right? And this thing is e to the negative epsilon size of z to the 3/2 times the cosine of 3 theta over 2. Right, 3/2 theta. Right, but the point is that 3 theta over 2 is trapped between 3 pi over 8 and negative 3 pi over 8, right? Because you just multiply it by 1.5, right? And it's trapped between these two bounds. Right. And if you're looking at the cosine, of that, well, the cosine of that is, the cosine of that is always bigger than the cosine of 3 pi over 8, right? So you have a lower you have a lower bound of that. Right? So this sine of 3 pi over 2 is bigger than or equal to cosine 3 pi over 8, right? And so that gives you that that this is bounded by something like this, minus e times some constant. That constant is your cosine 3 pi over 8. You get something like this, right? Right, you just combine the exponents together, and you get something like this. Okay, and the point is here that the z to the 3 halves is going to dominate the z. Right, so as z goes to infinity, this thing goes to 0. Right, that's the main point here. Right, so you see that this thing goes to 0 as z goes to infinity. Okay, so right, since this thing goes to 0 as it goes to infinity, you know that it's bounded. Right, because it's on this. It's defined on this sector, right? And you can take some large circle beyond which it's smaller than 1, say. Right, and then you're looking at the function behaving on some compact set. So it's going to be bounded on this part, and it's bounded on the infinite. It's bounded on the finite part. It's bounded on the infinite part. So it's bounded. Are you guys okay? Any questions? Any questions so far?
Is alpha just the cosine 3 theta?
It is, yeah. I should have just written it. Yeah. Okay, so now we'll show that it's not just bounded, but in fact less than or equal to 1. So claim, in fact, epsilon z is less than or equal to 1 for all z in S bar. Okay. So the proof is let M be the supremum, let me call it M sub epsilon, be the supremum of f epsilon for z in S bar. Okay. So we just let this be the supremum of the size of this particular guy. So then we know that there exist points Wj such that if you look at f epsilon Wj, then in size, those things will, in the limit, those things will go to m sub b, m sub epsilon. Right? That's what a supremum is. Right? By definition of supremum. Okay, so right. The observation to make here is that these points, these Wj, cannot go to infinity. Right? They can't go to infinity because the function goes to 0. The function goes to 0 outside there. Oh yeah, and without loss of generality, we can assume that f is not the 0 function. So these guys won't go to infinity, right? There's some value here. If they went to infinity, that would mean that the supremum would be 0. Okay. Does this make sense? Okay. They can't go to infinity, and so so there exists a limit point W. Okay. In S bar. Right. There exists some limit point of this collection of points. Okay. And from here we're basically done. We say, well, look, by the maximum modulus principle, W cannot be in the interior of S, right? Because if it were in the interior of S, then you'd have some open set, you'd have some open neighborhood around it, and then the open mapping theorem, which would mean would say that the value here could not be the maximum, could not be the supremum, right? That's how I hope you recall, that's how the maximum modulus principle, how we prove the maximum modulus principle. Open mapping theorem says, well, you can't be in the interior, right? So can't be in the interior, so that means that W must be on the boundary. Okay. But on the boundary, the size of epsilon is this thing times the size of this thing, right? Which we already saw here. Right, but this thing is smaller. This thing is smaller than 1, right? And this thing is also smaller, less than or equal to 1. Right? So in fact, we have it's strictly less than 1. Right. So actually, we have strictly less than 1. Right. And then as epsilon goes to 0, that gives us the bound that f must be less than or equal to 1. Now let epsilon go down to 0. F must be less than or equal to 1. Right?
Sorry, why is that less than 1?
Because this is just e to some negative number, right? Some strictly negative number. Right? So that tells us that right, that the size, that these guys are all smaller than 1, and so that tells us that this thing must be less than or equal to 1. That's when you take the limit. When you take the limit, you might get to 1. Okay, and that's the end. Okay, so this again was very clever finding the epsilon of room trick, where you're trying to show something about f, and instead you modify f to get functions for which the statement is true, and for which when you take epsilon go to 0, you recover the original function, and so that would imply the truth of the statement for the original function. Okay, Any questions? Yes, Joseph.
I don't fully remember the open mapping theorem and maximum modulus principle.
Okay, yeah.
But does the non-compactness of this set, doesn't impact the fact that W can't be on the interior?
No, because really, if you think about how we proved the maximum modulus principle, right? This thing is this is where the supremum is attained, right? This is where the supremum is attained. So if we, if it's in the interior, then by open mapping theorem, then we're going to have right. So like here this gets mapped. When we look at the modulus of f epsilon of this guy, we get m, right? But if by open mapping theorem we know that this thing is mapped, this neighborhood is mapped to an open neighborhood, which would mean that we're going to have values that are higher, right? So that can happen.
That makes sense. Thank you.
Okay.
We bounded by alpha earlier.
Mm-hmm.
Would it be sufficient just to notice that cosine is a bounded function when it's restricted to the variables?
Well, the trouble is that we don't want to get all the way down to 0. We don't want alpha to be 0. If alpha is 0, then we lose the decay at infinity.
Yeah.
Right? That would be bad, because what we want is for this function to go to 0 as this goes to infinity. So if we lose this term, then we can't. The whole second half won't work.
So you can't directly just adapt this proof to other sectors. You need to.
I think you can by changing the 3 halves, right? I think
That's right. Yeah, you have to
It
change.
only matters that 3 halves is bigger than 1.
Yeah, that's right. Yeah. Yeah. The okay. So let's see. So I think I'll let me do at least part of the last theorem in the chapter, which is about which is sort of like a Paley-Wiener, also sort of like a Paley-Wiener theorem. So it says the following. Suppose that f and f hat have moderate decrease. Then f hat is 0 for all c less than 0, if and only if f can be extended to a continuous bounded function on the closure of the upper half plane. So I'm going to write it like this, the closure of the upper half plane, such that f is holomorphic on the upper half plane. Okay, so this is kind of like the Paley-Wiener theorem. It's saying that again, right? That the support of the Fourier transform is related to how you can extend the function in a holomorphic manner. Okay. So so you start off with your function. It's defined only on the real line, right? And it's saying that if the Fourier transforms the Fourier transform is zero, for all negative terms, then in fact you can extend it to the upper half plane in this way. Okay, so the proof I'm only gonna show the forward direction. It's kind of familiar. You say, well, look, if you know that the Fourier transform is zero for all negative c, then you can use the inversion formula, right? So you use the inversion formula, and then you extend it to the upper half plane in this sort of obvious way, right? You say, well, look, you can get this guy as e to the 2 pi I x c dx, right? Because the inversion formula says that that it says exactly this, right? That you can recover the function by taking the inverse Fourier transform of the Fourier transform, right, over the line. But this thing is supported on 0 infinity, so we just have to we can truncate it. Okay. So and then then extend to the upper half plane, and you'll see why we need the upper half plane. In sort of by just extending this to to complex numbers. So by this f hat c e to the 2 pi I z c dx. Right. So by using the if you want the holomorphic Fourier inversion. Okay. And the point is that this converges. This integral converges because of the decay, right? You know that the size of this is controlled by, this term is controlled because of the moderate decay. And then this thing is going to give us the e to the negative 2 pi y c dx. Right. So we would be in trouble if y were negative, right? Because then we would have this exponential term on it. But because y is positive, this thing decays. Yes, Noah.
Is y the imaginary part of z?
Yes.
Okay.
Right. So here's where we use that y is bigger than 0, right? To get that this thing is bounded by just the normal, our usual bound. So in other words, this integral actually does converge, and in fact we've simultaneously shown the boundedness of it. Okay. Now, the rest of it is just sort of sketched out, I'm afraid. You take, right, we still need to show that this thing is holomorphic. And so what you do is you, similarly to what we did before, you truncate the integral. Right, so let f sub n z be defined as this thing, where you're integrating up to n. Okay. As before, these guys are holomorphic by the theorem that we've cited multiple times. Okay, and so one shows that these guys converge uniformly to f, and so that will give that this thing is holomorphic, because you've got the convergence of the holomorphic functions to this thing, and also that would give that would also show continuity on the line, because uniformly convergent continuous functions converge to a continuous function. Okay, so I'm afraid that's all I'm going to show that. The rest of it is just almost left as an exercise. It's just, yeah. Okay, so yeah, so that's it for the Fourier connections between complex analysis and Fourier analysis. So the next part is to the theory of entire functions. And one of the main tools we're going to use here is called Jensen's formula. Okay, so Jensen's formula you want to think of as, so let me see if I can sort of motivate Jensen's formula. Okay, so suppose you have a function g that's holomorphic on a neighborhood of the closed unit disk. So it's holomorphic on a neighborhood of the closed unit disk, and G never vanishes. Okay, it's never 0. Okay. Well, in that case, we can consider the log, right, of the absolute value of G, right, as you may have seen in your homework, that's the real part of the log of G. Right, that's the real part of the log of G, and so so this is a harmonic. So we get a harmonic function. Right. Okay, so one thing that we saw before is that if you have a harmonic function, then the mean value property still applies to the harmonic function, right? And so we can, the mean value property, we get the following, that the log of G of 0 is controlled by, is equal to the integral, so the average value, right, the mean value of the function on the boundary of the circle. Okay. So this is just the mean value property. Right. right? So it says that, yeah. Question? Yes.
When did we learn about the mean value property? Was that on the homework or was that an earlier section?
We did that.
Remember?
I think it was on the
I think it
homework.
came up on.
Okay.
This thing definitely came up on the homework.
I think I actually did it. I mean, this came up on the homework, but I think I believe I did it in class, but I'm not sure. Yeah. Right, you just take the Cauchy integral formula. Yeah. Yeah. And then, you know, for harmonic functions, you take the real part. You take the real part of the Cauchy integral formula, and that just gives you the formula. Yes.
How do we know that the real part of the log is harmonic when log is not entire?
Well, G never vanishes,
Okay.
right? So we never have.
Oh, I see.
Yeah.
Okay.
Yeah. Otherwise, we'd be in trouble. Yes. Okay. So Jensen's formula. The idea for Jensen's formula is basically do this for arbitrary holomorphic functions. Okay. Can we come up with such a formula for arbitrary holomorphic functions? Yeah. Okay. And so the tool that we're going to use here to create this tool is something called the Blaschke factor, which you encountered on an early homework assignment. So let me redefine that. So for any point A in the unit disk, define this function b sub a by b sub a of z is z minus a over 1 minus a bar z. So this b sub a is called a Blaschke factor. So I'm following not Stein's presentation, but a presentation in a different book by Green and Krantz. If you want to look at it. Okay, so I think this is kind of a prettier way of thinking about it. So theorem, just some properties of the Blaschke functions. One, they are holomorphic on a neighborhood of the closed unit disk. They have one and only one zero at A, and it's simple. And three, the size. If you take a point on the boundary of the unit disk, excuse me, then B sub A maps that again to the boundary of the unit disk. Okay, so these are pretty straightforward. You say, well, look, if we look at the denominator if we want to show this thing is holomorphic, let's look at, if we look at the denominator of the Blaschke factor, right? We see that, you know, 1 is going to be a bar z, if and only if, of course, z is 1 over a bar. But 1 over a bar, so that tells you that B sub a is holomorphic whenever z is, absolute value of z is smaller than the absolute value of a, 1 over the absolute value of a. Right, so that you can never reach this point where the function goes bad. Right. A is some point inside the unit disk, right? 1 over the absolute value of a, you know, is some greater radius, right? And as long as we don't reach that, we don't reach that radius, the denominator is never going to vanish, right? So you're holomorphic on something that contains the unit disk. Okay. Number 2 is kind of obvious, right? Clearly, clearly this thing is has a simple 0 only in A, right? So. Right, because it's z minus a times some holomorphic function that doesn't vanish in that neighborhood. Okay, and then part 3, right? If we're looking at if the absolute value of z is 1, and we're looking at this sort of thing, then you can multiply by z bar, which is 1. Right? Right. And that would give us zz bar minus az bar over 1 minus a bar z. Right, which is just 1 minus az bar over its conjugate. So that's what that was. Okay, so now we're going to prove Jensen's formula. Okay, so let me lay it out here. Here's the statement. Okay. So let F be holomorphic in a neighborhood of the unit disk, I'm sorry, of a disk of radius r. Okay, and suppose that f is not 0 at the origin. If the zeros, no, if the set A1 through AK contained in the open disk counted, so are all the zeros of F in the closed disk. So there's nothing on the boundary. Okay, no zeros on the boundary. Okay. And these are the only zeros inside the interior, counted with multiplicities. So if there are multiple copies, you just count them as additional zeros. Okay, so then the following formula, log of f of 0 plus sum of log of r over aj in magnitude, as j goes from 1 to k, equals the mean value. Okay, so it's basically like the previous formula, except you have this additional factor. Yeah.
Stine's book gives it with the sum of the log term on the other side of the equality.
Yeah, with the term with this thing inverted.
I see.
So it's the same thing. It's the same thing. Yeah. Okay. So the proof is to use the Blaschke factors to create a non-vanishing function. Okay, create a non-vanishing holomorphic function. So we create a non-vanishing holomorphic function on the closed disk. Okay, by using the Blaschke factors. Using the Blaschke factors. So well, let g of z be the original function, but now divide by the product of the Blaschke factors scaled to the disk. Okay, so you scale the Blaschke factors so that now they're scaled to the disk of radius r. Okay, and you set them up so that they're going to have zeros at the a sub j's, right? Right. So when z equals a sub j, we're going to the Blaschke factor has its 0 there, right? So we create this function. We create this function which has zeros exactly and only at the places where the guy on the top has its zeros. And so that cancels off the zeros, and we end up with a non-vanishing function. Okay, that's the main trick. And then we just apply the baby formula that we got before to this, and that out pops Jensen's formula. Okay, that's basically the idea. Okay, so create a non-vanishing function by dividing out all the by canceling out all the zeros, and then apply the original formula that worked for non-vanishing functions. So observe that b sub aj over r, z over r is holomorphic on the disk of radius r. It has a 0 of order 1 at aj and nowhere else. Right, and so g is a non-vanishing holomorphic function on the disk. Okay, so now it's pretty straightforward. We just apply the Bailey formula to this G, right? So the simple version, the simple formula gives us that the log of the absolute value of G at 0 is equal to 1 over, you know, log G RE by theta into theta. I probably should have said that, you know, I guess it's obvious, but we can say that that original formula works when we scale it to a disk of radius r, of course. We didn't have to stay on the unit disk. Right? But here we get the log of the absolute value of this quotient, right? And so by properties of the log, we get that, you know, this thing on the left-hand side is just equal to this minus the sum of the logs of the Blaschke factors. J equals 1 to k. Right? And then on the right-hand side, we're going to get, well, we're going to get the you know, something similar, right? We get the log of the function, the original function, minus the sum of those average values for the Blaschke factors. Everybody okay? We just use properties of the log. Okay. Now, what's this? 0. Right? Noah.
What I was going to ask is, like,
Yes.
for logs there, you mentioned before that when we're taking a log of a real number, like, we use ln rather than log. Is there a reason we're not doing that here? Because we're like that is just the regular real natural log, is I guess what I'm asking.
You're right. You're right. I should. This is just a real natural log. Yeah.
Okay, cool.
So, as Noah pointed out, well, look, you know, this thing is of size 1, and we said earlier that the Blaschke factor maps things of size 1 to things of size 1. So, you know, the size is 1, we get the log of 1, that's 0. Right? So this thing just vanishes. Right? So the only thing we have here, the only thing we have left is to show that this thing is the same thing as this thing. Okay, but that's just a calculation. Right? You know, log of Baj over r of 0. Well, I guess I erased it. Is going to be log of 0 minus aj over r over 1 minus the complex conjugate of aj times 0. Right? So that just gives us log of aj over r. Right, and so that's why this has a minus sign. That's why this has a minus sign on it. Right, this is of course negative log r over aj. Right, so we get that this thing equals that thing. Okay, so that's the proof of Jensen's formula.
So the function can't have a 0 at 0.
That's right. That's right.
Or-
Because then this wouldn't make any sense. Yeah. Yeah. So you don't want to do this at a 0. So this formula actually can be extended to an arbitrary point. Right? It doesn't have to be at the origin. You can do it at an arbitrary point. The formula gets modified slightly, but you can do it at an arbitrary point that's not a 0. That's not a 0. The formula also has an extension to the case of meromorphic functions. So, like, you get some other factor that comes from the meromorphic functions. Comes from the poles. Okay. So in that case, you don't want it to be a 0 at a pole, or 0 at a pole. Okay.
I thought we picked the Blaschke factors because they have simple zeros or I thought we wanted simple zeros at AJ, but wouldn't these have simple zeros at AJ over R? Oh, our input is Z over R?
The input is Z.
I see.
Yeah.
I see.
So this is the function Z goes to the AJ over R, Z over R. So when you put in an AJ, when you put in AJ here, you get a 0.
Right, I understand.
Okay, so this actually gives, as an immediate corollary, there's something called Jensen's inequality. So you notice that this term is greater than or equal to 0, right? You know, these things are all contained. These things are all of magnitude less than r. So these are all positive numbers. Okay. So what does that tell you? Jensen's inequality that the log of f of 0 is dominated by the right hand side here, by this term. Or, if you like, same thing. This is smaller than e to this thing. So this is an inequality that sometimes comes in handy in analysis. Okay, everybody all right with that? I think it's kind of a cute proof, right? You just start with a simple version, right? And then you say, well, look, if my function has if my function has zeros, then I can get rid of those zeros by using the Blaschke factors. This thing on the bottom is called a Blaschke product. Right, because it's a product of the Blaschke factors. You can imagine what you do if you have poles, right? You just throw on the additional Blaschke product on the top to cancel out the poles on the bottom, right? And then you apply the baby formula to that, and then the formula pops out again. So, okay. I think I have enough time to get to the last thing here, which is regarding this term. There gives you a geometric interpretation of this term. What does that term mean? Okay, so what is that? What is that term? So let me introduce some notation. For f, it's holomorphic on the the closed disk. In other words, on a neighborhood containing that closed disk. Denote by, so notate n sub f of R as the number of zeros of f in D sub I 0. Okay, so it just records the number of zeros of f. In, right, you have, your function is defined on some radius r. You're seeing as the small radius increases, how many zeros are in there. Right, so it just counts the number of zeros of f. And the lemma is that that this factor, that if you look at the integral of n sub r against dr over r, then that actually gives you that factor. Okay, where z1 and zn are the zeros in D sub r. Right, and so the consequence is going to be that the consequence is going to be that that this integral here is the difference, right? Is how much bigger this is than this, right? Jensen's inequality tells us that this is less than or equal to that, right? This is less than or equal to that, and then how much bigger that right side is than the left side actually measures how many zeros you have in the disk integrated against this dr over r. Okay. So okay, so let's prove that. Right. So you say, well, we're looking at the integral. Yeah, let's do it this way. We're looking at this integral here, right? But if you think about n sub r, what is n sub r? It's just counting the number of zeros, right? So one way of thinking about it is that n sub r is the sum of the characteristic function of the interval size of zk infinity r. Okay, so characteristic function. So when I say like the characteristic function of a, it means you get 0 if x is not in a, and it's 1 if x is in a. Sometimes called an indicator function. So you take these guys, right? So when you look at the size, the size of each of the zeros, you look at the size of each of the zeros, right? And you say, okay, we're going to create this function that is 0 before then, and then it's 1 afterwards, right? Is 1 afterwards. And if you add up all of those guys for the zeros, well, that's the thing that counts, that's the thing that counts how many zeros you have in a circle of radius r, right? Once your r right? Once your R crosses the size of this 0, you've got 1, 0, right? So you just add up all of these things that, each of these things counts as zeros, so you add up the things that count the zeros and you get this thing. Okay, I hope that's clear. So in any case, you get this thing, right? So this turns into the sum from k equals 1 to n of the integral of the characteristic function of the characteristic functions. R dr over R, right? But what's this? Right? If we, you know, I pulled the finite sum through the integral, which is fine, of course, right? But you know, what does this thing do? This says that we're going to take the integral. This says that we're going to take the integral from the size of zk to r of dr over r. Right? Right? Because you know, this thing is going to be 0 before the size of zk, and it's 1 afterwards. Right? So what does it do to the integrand? It says, well, we're only going to integrate r from zk up to r. Right? So you get the integral of zk up to r of this thing. Right? But that's, of course, the summation of log of r over zk. Right, which is that term. Okay. So this thing basically measures, you know, how much bigger this term is than this term. Okay, that's it for today. So, see you guys later.